Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Texas Instruments. We have Arnon Friedmann, and Arnon is the business manager for HPC at Texas Instruments. So, Arnon, welcome to the show.
Thanks, Rich. Thanks for having me here today.
I never have really associated TI with HPC, and you're the business manager for that. Is that a new position?
Yeah, it is. You're not alone in not associating DSPs with high-performance computing. So, I'm excited here to talk about, why we're making that association and what we see as the role for DSPs in this market, and kind of why we see a play here. But yeah, so for a long time, our multi-core DSPs were used in networking and wireless base station infrastructure at really high-end, high performance, but mostly with fixed point. And recently, and I'll go into this in the podcast, we had a floating point to our DSPs and found that we have something interesting here. And so I was carved out of our wireless team to go explore opportunities in high-performance computing for TI.
Oh, terrific. Well, I brought your slides up here so I can follow along whenever you're ready.
Yeah, so, our header slide is new lows in high-performance computing, and by that, of course, we mean power consumption. So, coming from the embedded space, and as I alluded to in the wireless market, in the base station market in particular, where these DSPs are coming from, power consumption has been key in being successful in that market for a long time. So, we're really coming at it from a performance per watt basis, and we think we have an interesting solution. So if you go to slide 2, we're unleashing these multi-core DSPs onto the world, I guess, instead of just into our particular segment, where we'll show that we have the lowest power consumption per megahertz, gigamac, or gigaflop, and that's really the key. The key here being that we're able to do floating point, whereas our multi-core DSPs in the past really, this was launched back in sort of November, December of last year. We were really a fixed point at the high end previously. So, moving quickly to slide 3, this gives you an idea of what we call our Keystone multi-core architecture. So all of our multi-core DSPs now are being launched off what we call the Keystone architecture, allowing us really to, as in that previous slide, say, unleash the performance of multi-core. And, we've been doing multi-core for a while. We've been very successful in wireless and networking markets. And some of the things that we learned were that it's sometimes challenging to get the full performance out of a multi-core system. And so our Keystone architecture is really focused on making sure that when you do start putting aggregating a lot of cores together, that you truly get, n times the performance of a single core. And so, briefly walking through this slide from top to bottom, overlaying the top of everything is something we call a multi-core navigator, which is effectively an atomic hardware queue that allows the cores and peripherals to interact together without requiring a software manager to handle conflicts or contention between cores and peripherals. So it's sort of a hardware feature that we added that allows non-contentious sharing of resources, and that was one key element. Going down, the second key element there in red is multi-core shared memory controller, again allowing the cores to access both 4 megabytes of shared memory in the device that I'll be focused on, as well as going directly to off-chip memory and accessing external memory quickly. So, again, it's a new feature from before, but again, it's all towards unlocking, multi-core architectures. And then stepping down, you see we allude a little bit to things dealing with our wireless background. Some of these are available in different chips, so you'll see in our DSP multi-core, what we call the C66 architectures. There's some chips targeted at pure compute, which is what we're looking at for high-performance computing, and some devices targeting other markets. I think the last thing I'll mention really on this slide is to the left. You see what's called the TerraNet. And this is a really high-performance switch fabric, which, again, if you're not careful in how you architect a multi-core system, you can get a lot of bottlenecks internal to the device. And the TerraNet is a non-blocking switch fabric that has 2 terabits per second. And that's, hopefully, I haven't bored everyone already with the detailed discussion of the chip right away. So going to slide 4, we'll step back now a little bit outside of that, talk about what we have here. So performance and value is is what we talk about for these DSPs. And really at the top of this, you see the C66X multi-core DSP. And this C66X, and this is again announcements if you go back and look, made earlier this year and late last year, was really this new DSP core, which does both fixed point and floating point on the same core. You can go back and forth between them seamlessly. It's just instruction calls. And on the floating point, when the C6678, which is really the chip that we look at for high performance computing, has 8 cores. There's 20 gigaflops per core. There's 160 gigaflops per chip. When you look at other DSPs in the market, there's just nothing out there that compares. So clearly, going into high performance computing, we're not going to be looking at other DSPs. But in the market segment that we were in, as far as DSPs are concerned, it's very interesting there. And now as we take it into the other markets, we're finding that it's pretty interesting there as well. So if we go to slide 5, fixed and floating point math in every core, and we call that floating point at fixed point speeds. And so this is 1 gigahertz, 1.25 gigahertz, just really powerful, low power consumption, floating point math, which is, as we're learning, very important in high performance computing. So going to slide 6, again, we've been focused for a long time on low power, so green systems. And we have a technology called Smart Reflex that helps keep our DSPs lower than any other DSP. And when we look at competitive devices for floating point performance, we believe we have the strongest one there. So, for example, the C6678 provides 16 single precision gigaflops per watt, which is better than any metric I've seen in a competitive device, at least anything that's in production. There are maybe some startups and others that might claim something, but when you look at a production device, which this device is, there's really nothing out there that's at that level today. So moving to slide 7, this is giving you a broad range of markets where this DSP goes, and really what we want to emphasize is that our multi-core DSPs are product and field tested, and they have been for a long time. Again, this isn't a new architecture. It's just bringing floating point to a proven and existing architecture. So, we see a lot of success in mission critical markets. Radar systems, in particular, are one really big area for us. Test and automation. There's a lot of high performance imaging and cameras that are looking for defects, whether they be in semiconductors and LCDs, a number of different devices. And you can see a lot of high performance DSPs being used there. Medical imaging is another area. Ultrasounds, digital X-rays, especially in operating rooms where real time is critical. High performance computing. We'll talk even more about that as we go through this presentation. In broadband, this can be anything from emergency wireless networks set up in disaster zones to greenfield deployments where they don't have anything but wireless to deploy. And then smart grids is another area, and video, a number of different sort of network-centric places for DSPs. So that just, again, we want to emphasize that these DSPs are, production ready. They've been proven in a lot of complex systems today. And so, as I like to say, it's not a matter of, will the device work? It's a matter of how good is it for the market. So I don't think, we really only have to answer the question of, how good are the DSPs in high performance computing? If we can show that they're good, then we know, hands down, that we can build good products out of these devices. So if we go to slide 8, traditional HPC markets, well, what are the needs of the developers? They need fast and efficient systems. The areas, I think these are traditional areas that we all know: oil and gas, finance, molecular dynamics. But one of the things the DSP brings that is somewhat different than what we're competing against when you look at acceleration for high-performance computing is that we have a standard programming model. So oftentimes in those systems that I showed before where the DSP is used, the DSP runs the entire application. So, we're not just used as an accelerator to some general-purpose processor. There's no CPU. Our programmers write entire applications in C code. They compile it and they run. We don't need assembly for our DSPs anymore. We have very good compilers. So one of the things that we're bringing here is saying, hey, you can use us for acceleration. You can use us for the entire application. There are areas in larger systems where CPUs, we believe would still play a role, but a lot more of the application can be offloaded to a farm of DSPs, let's say, than maybe just traditional acceleration if you look at what GPGPUs do. So we believe not only are we bringing a lower power story, we're bringing ease of use to the system. So then going to slide 9, gives you sort of a picture of what we're talking about. The chip itself, the C6678, is shown on the left. It has 8 DSP cores in it. Each core runs at 1.25 gigahertz, and it provides equivalent of 10 gigahertz, but each core is 20 gigaflops, and so 8 cores runs at 160 gigaflops. So you have 160 gigaflops at 10 watts for this chip, and so that gives you the 20 gigaflops or 16 gigaflops per watt. And then we have available today, we have a PCIe card that's a half-length, single-width PCIe card that has over half a teraflop, 500 gigaflops, 512 to be exact, gigaflops of performance at only 50 watts. Again, if you look at the market today for high-performance computing acceleration, you'll see maybe 1 teraflop at something to 250 to 300 watts, and you'll see it at a full length and double width. So from a power consumption standpoint, from a size standpoint, this is a much smaller and more efficient card than what's available on the market. And then soon we'll be launching a full-length card that has 8 DSPs and a teraflop of performance. And so, you have the sort of the typical use that people are familiar with. You can plug it into an expansion slot. The software case now can be different, though. It could be used as an accelerator, but it can also be used to offload a much bigger piece of the application. And so looking at slide 10, we talk about some of our software tools. We have an Eclipse-based visual editor in Studio, a full debug, so you can step through code, you can step line by line. Again, I believe in some of the current accelerators, the debugging capabilities aren't nearly as powerful. We've had, as I mentioned, many years of experience with this, and in some of our systems, I can just give you an example from the wireless base stations where it's not uncommon for us to launch a system and months will go by and years will go by and people will suddenly see maybe a bug that happens or an error that happens in their code just once per month. And so we have debug capabilities that can allow you to, instrument the code and catch things like that. So very powerful debugging tools, which I think is far surpasses what you normally see in this market. And then we also have a lot of the optimized libraries. So I think, standard for the market would be linear algebra libraries, FFT libraries, image processing libraries, really providing optimized code to the user so they don't have to worry about, how do I optimize my code for this architecture. You just take your C code, pull in the libraries, and you're up and running. We believe very, very quickly. I'll also add that we support OpenMP. We're the first DSP to support OpenMP in the market, but it also aligns us much more closely with x86 architectures, which often use OpenMP to exploit parallelism. Going hand in hand with OpenMP is a software structure called message passing interface, MPI, which is also something that we support. So sort of the traditional high performance cluster compute, supercompute programming models are supported in the DSP. And another reason why we think we're very interesting for developers in this market. So I guess just to recap, slide 11, we have this new Keystone architecture. We have this new C66, the most powerful DSP core in the market today. Adds floating point. It's low power. And so the other phrase I like to use is that, providing a new paradigm. So from what I've seen in high performance computing, there's x86 architectures, there's GPU architectures, there's some FPGA architectures, but not as much. And now I believe that DSPs are really, should be part of that conversation. When people look really deeply at what we have, I think they'll see some advantages and consider us in that conversation now. So slide 12 just gives you a view of, hey, where can you go to find out more about this? So you can go to ti.com/multicore or /C66 multicore. We have an Ask the Expert videos where you can learn more. We have a multi-core mix blog where a number of us talk about some of the developments in our multi-core technology. So anyway, so you can spend some time with this slide and maybe follow some of the links if you want to learn more to see what we're doing. And then finally, on the last slide, I'd like to say thank you again, Rich, for letting me talk to your audience here, spending a few minutes. And please don't hesitate to dig a little bit more into this and to contact me or others at TI and see what we can do to help you out.
Well, thank you for that, Arnon. A couple questions here. I'm looking at this. Seems really interesting in that you've got this low power and extreme floating point, and then you talked about the programming models, and that's of course that's really important to the listeners for this podcast. How onerous would it be to take, say, an x86 code written in C and get it running on this kind of device?
So first, let me take exception with how you phrased the question, which was how onerous. So I think you're just too used to talking to our competition. So we don't believe it would be onerous at all. Actually, if it's C code, it should come over and compile right away. Now, of course, to get full advantage of the 16 gigaflops per watt, you are going to need to align to our libraries, which should standard interfaces. If you're using OpenMP, then it should just come right over. There'll be some work, if you're in a standard sort of acceleration model today and you're modifying to use with the DSP, then there'll be some APIs that we'd have to adjust. But in general, I would expect it to be relatively straightforward. And it's, a lot of what we're doing now is we're working on demos of exactly that, of, going out and finding x86 examples and bringing them over and running them on our PCIe cards so that we can show people that it's really fairly straightforward and not at all like what they're used to over the past few years with some of the other architectures out there.
So what are the application characteristics that are going to really shine on this device?
One of the things that we found, because there's a whole slew of benchmarks out there for high performance computing, and in our early explorations of going through them, and we are, I will admit, in sort of the early explorations of this space, FFTs, for example, run really, really well on the DSPs. Mm-hmm. We're looking at the linear algebra functions are running quite well, and we're trying to roll them up into larger architectures. And I guess the one other thing I would add is the DSPs have a lot of high-speed connectivity on them. And so I think one of the, if I talk mostly about PCIe cards just because we're sort of following the industry and where it is right now. And one of the challenges, as I understand, is that you would send a lot of data down the PCIe card, but if you have more data or more processing than for one card, then sometimes the PCIe cards have difficulty communicating to themselves. So some of the things that we're looking at is we have a number of different interfaces. So we have PCI Express. We have something called Rapid I/O, which is used in a lot of the high-performance telecom. We have a custom interface called Hyperlink, which runs even faster than both of those. So we're looking at some novel board and blade architectures where we'd have a lot better interprocessor communication, and we could, rather than this model of host sending to PCIe card and then having to navigate data going from PCIe card to PCIe card in bigger systems, we could have a backplane based on Rapid I/O, for example, that would allow all the DSPs to talk directly with each other over different interface and still go to the host over the PCIe. And so there we think we have some interesting advantages as well. But in general, I think where you're really concerned in systems where we're really concerned about power consumption, I think we're seeing, depending, again, like 4x improvements over what's been published in linear algebra. Maybe it's 6 or 8 times better in FFTs. I haven't seen an application yet where we haven't been able to maintain that power per watt advantage over something that's been published yet.
Mm-hmm.
Wow. So I'd say all the traditional markets, the computational finance, the molecular dynamics, computational chemistry, oil and gas exploration. I haven't seen anything that said, okay, we're limited to this particular area. Now the DSP itself is interesting because it scales down, from what people use in high-performance compute. And what we see in high-performance imaging and some real-time imaging applications is that sometimes some of the traditional HPC solutions are overkill, and the DSP fits, like a glove in those architectures because there isn't too much that competes with us. That I would say is sort of this lower end imaging analytics opportunities that we're starting to see in the market too. But I don't consider those traditional high performance compute opportunities. I'm just sort of mentioning that as an aside.
Sure. So, Arnon, you're the business manager. So if everything went right, what would you foresee? What kind of platforms would we see built around this?
Well, really what I would like to do and what I'm working towards is I'd like to see all the major server vendors out there have a card that's a TI DSP card, a blade that fits into their servers, and is offered as another high performance compute platform. So that's what I'd really like to see. I mean, clearly I'd like to see customers buying lots and lots, right? But that goes without saying. But yeah. I think we'll know that we've been successful when somebody clicks on a server manufacturer's high performance compute line and there's an option to select the TI blade.
So, Arnon, we got SC11 coming up. Is TI going to join the fray and be there?
Yes. Please come out and visit us. We'll have a booth. We'll be in booth 4200. We'll be demoing both that low-cost EVM I was telling you about. We'll also have the PCIe card with the 4 DSPs, and we'll be running our benchmark code on that as well. So yeah, please stop by, introduce yourself. I'd love to talk to your listeners about what we're doing and how they can get started and work with a pretty cool new entrant into this market.
Terrific. Well, Arnon Friedmann, business manager of HPC at Texas Instruments, I want to thank you once again for coming on the show today.
Yeah, thank you, Rich. Really appreciate it.
All right, man. That's it, folks, for the Rich Report. Stay tuned for more news and information on high-performance computing.